This is the 10-Minute Teacher Podcast, episode 680, Mathematical Modeling on Trial and the Math's Fix, featuring Conrad Wolfram. Welcome to the 10-Minute Teacher Podcast, hosted by author, educator, speaker, and mom, the Cool Cat teacher, Vicki Davis. Today, we're super excited to have Conrad Wolfram, CEO of Wolfram Research, with us as our special guest. Wolfram Research is responsible for Wolfram Alpha, demonstrations, and the core underlying technology, Mathematica. Conrad founded the European Wolfram Research in 1991 after his brother Stephen set up the headquarters in the U.S. He is also the founder of ComputerBasedMath.org. Vicki and Conrad are speaking about some problematic issues arising in today's math. Let's join them now. Enjoy!
So today, remarkable educators, I am delighted to be talking to Conrad Wolfram. As a numbers person myself and a person who enjoys math, as we say on this side of the pond, this is a fascinating topic. I do have an advanced reading copy of your new book, Conrad, The Math's Fix. And you have a few issues with where we are today with math. So could you just give us a big picture of why is math today broken, besides the obvious reason that many kids just hate it because of what we've done to it?
Yeah, sure. It's great to be here. You know, the real problem with math right now is we're making humans do what the computers should do, and that's the calculating bit almost entirely. And in real life, you use math to do fantastic modeling, and we're seeing this with COVID, sometimes right, sometimes wrong, and work out all sorts of things about life. That's done because we use computers to do the calculating. We use our students, our humans, to do setting up the problem, abstracting it, interpreting it. But we're not doing so much of that in school. And that's also, I think, making a lot of students hate it for no reason when they could really enjoy the kind of things they can work out from it.
You say that no mainstream school maths curriculum has yet been reimagined and implemented based on the obvious assumption that computers exist. And, you know, when calculators were first invented, if you look back at the material in education, they were considered evil, even though my husband, who's an engineer, couldn't live without his calculator. How do we reimagine? Where do we start from?
Start from real problems that people do with math and computation in the real world. I mean, the reason we're so concerned about our students being good at math is so that they can have good jobs, so they can involve themselves fully in society. And we need computational literacy for that. You know, the same way we have literacy, we need everyone to have some idea of computational thinking, ability to apply a computational process in their lives. But the way they do them in their lives now is with computers on complex problems, not on toy problems where they have to do it all by hand. So we need to start from those real problems. We then need to work back and see where and how we applied the math using computers wherever we want to do the calculating, often of much harder problems than we do in education right now. And that's, in a sense, the starting point.
Well, I'll give you an example. I was in a 10th grade classroom back before I was a classroom teacher doing some consulting for that particular school system. And she was teaching basic subtraction of very large numbers with no calculator. And they're working a problem. And she said, now, how do you write that on the board? Okay, you know that you have to put the larger number on top because you cannot subtract a larger number from a smaller number. And I was sitting there thinking, these kids are 2 years or 3 years away from managing a checkbook. Yes, you can subtract a larger number from a smaller number.
Yeah, absolutely. You see, when you look at these things, the problem in there is, do you know how to set up the problem correctly? Did you know it was a subtraction problem? Or did you know it was a multiplication problem? Or did you know you needed machine learning for this problem rather than data science, rather than statistics? Once you've abstracted it and set it up right, in your example, a subtraction problem, whether the bigger number is on the top or the bottom, we have computers, calculators, smartphones, the rest of it, to do the actual calculation. So that's not the bit we need to be worrying about so much. We need to be worrying about that setup. When we get the answer out with a minus sign in front of it, what does that mean?
Yes.
Can I interpret that? Does that mean I need to borrow out of my account? You know, so those are the real things. It's the abstraction, as we call it, the setup of the problem. Then we've got step 3, which is the calculating. And that's the bit that usually can be done by a machine. And then we got step 4, which is, okay, we got a number out. What did it mean? Or we got a piece of algebra out. What did that mean? Did that connect with our original definition? And if not, could we have been fooled by something? Do we need to redefine it? Do we need to go around it again? And in the book, I talk a lot about these 4 steps and also what we call a helix, which is you go up the 4 steps many, many times to refine your answer. Because in the end, all of this math, all of this computational thinking, it's all to get to better decisions. And that's what we've got to help folks to do using this fantastic process of math and computation.
You say that machinery has mostly replaced a human brain, but not the human brain. And for example, when I work with students who are struggling with math, I will send them to your search engine because you can type in a math problem. It gives them all the steps and they can work through it, because one of the issues that students have is there's just not enough problems in the maths book to be able to understand what they've done. And you, of course, give it to them step by step. Now, there's some educators who argue that's, quote, cheating. I mean, you've heard that before, right? What's your response?
Well, it's only cheating if you have the wrong problems to solve. And if you're not applying your mind to what you really need to get the right answers. A very early TED talk I gave in 2009 was, is it cheating to use Wolfram Alpha for my math homework? And I addressed exactly this issue. And that was a forerunner to some of the work I've done since. You see, the thing is, we need people to be confident. I think confidence is really important. We need them to be able to actually solve the problems they're going to come up with in life. And those problems tend to be rather harder and messier than we tend to have. And so actually giving them experience by doing lots of problems, even if it's on a computer, even if it's with a traditional math curriculum in the way that we're doing it, just that confidence and experience can improve their outcomes. And, if they then need to learn how to do it for the test by hand in some way, they'll probably have the confidence to push through that much more. A lot of the problem we have, particularly people who hate maths or come from a more disadvantaged background, they don't have the confidence to push through the abstract ideas first. And that's such a pity, because they're often really good thinkers. They often have really good abilities underneath. But the folks from slightly more affluent backgrounds and things can often have that ability just to push through this abstract bit they didn't really understand and get to, if they're lucky at the end, the practical application. We need to switch that completely. So we start with the practical application and then work back through why the abstraction and the math was helpful.
Now, in your section, Roadmap for Change, you take issue with the PISA test, and I'll just read that it assumes no global systemic misunderstanding with the worldview of math. So basically, PISA measures compliance with the current worldview of math, but you're not entirely sure the current worldview is correct.
Exactly. I mean, it's a common problem in many areas, and math is right at the top of this in education. We have a worldview of math that it's primarily about hand calculating in education. And my argument is, as we enter the AI age, that is less and less true. It's mostly about this fantastic process of learning how to computationally think using the machinery we have. And we have invented these fantastic machines. They do things billions of times better than we do in many cases, but we can use those and climb on top of those to go further. Now, if we have the wrong view of math, what we do is subjugate humans to be, in a sense, third-rate problem solvers, third-rate human calculators, when what we really want is the humans to be the first-rate problem solvers. So what we need there is first-rate human problem solvers, not third-rate human calculators. And in a sense, PISA and every curriculum around the world assumes a math curriculum built before calculators and computers really existed. They've adjusted since then, but the fundamental assumption is it's to learn how to calculate. And that was the sticking point for hundreds of years for the use of mathematics. So it's not illogical that that's how it should have been before. It's just in the last 50 plus years, we got the machines to do that bit of the 4 steps. And so now we can go much further, much faster, much more relevant to the real world. That's what's driving us to need this mathematics anyway.
And as my engineering husband often quotes Deming, he says, you get what you measure, but that's likely all you'll get. And that's the issue with having the wrong measure. Now, in the current situation with the COVID-19 crisis, and a lot of us are actually imagining what the fall is going to look like, does AI have a place with teaching maths as students may be at home or at least separated from their teachers somewhat? What could school look like in the fall that would perhaps let us apply some of this?
Well, first thing to say is if people are working remotely through a computer, we know they have a computer. So that's a good start. So let's then use the computer to do a broader range of experience and mathematics and, things where they can calculate big numbers and use data, etc. And so we've put up some modules, more traditional things, but also things connected with the computer-based math. And we got those free at the moment in the middle of the pandemic. We're obviously keen to get everybody engaged. So that's one thing. I think use the computer not only just to do the online learning, of the form that you would have done before, but we can now assume the computer. So let's go out of the pre-computer age and start actually trying, let's say, data examples with really big numbers, really big amounts of data, I should say. So I think that's one way to reimagine. I think the other thing is the ability just to mix together, trying lots of things, doing little bits of coding. What I'm talking about, by the way, here is much beyond coding. But of course, being able to do bits of coding to get your maths further is a great advantage too. So those are a few of the immediate changes I can see we could do and really help supplement what's there at the moment.
Well, we can move and iterate so rapidly. I mean, combine the maths knowledge with surveys and the ability to do a Google form. I mean, kids can do a Google form, literally have hundreds of responses and start analyzing that data.
And that's a great way to do things. That's a great way to see the practical. Also, with our Wolfram Alpha, you can pull in computable data straight away. And particularly if you've got Mathematica or our new Wolfram Alpha notebook edition or any of those things, you can then work with analyzing that straight away with real world, it's often live data. And that's pretty exciting.
So fill in the blank. One thing that I wish every maths classroom in the world would do in the fall is, well, besides use Wolfram Alpha.
I get that. Put up a poster, which we have, of the 4 steps of computational thinking. And whenever you're doing math, be really clear which step you're in. Because I think knowing how to get that process, whether or not you're allowed to use calculators and computers for step 3, the calculating step, it really helps you to get really clear on what you're doing, when you're doing it, even on problems where you don't need to break it down. But then when you get to the harder problems, you don't get so easily confused. So I think that's a really helpful thing. You can get the poster to download. And of course, the other great thing is if you're a teacher, take a look at my book, because I think even if you can't implement everything there, because the curriculum doesn't allow that, I think it will give you a background of why we're doing the maths we're doing, and hopefully give you as well as the students more confidence in today's maths.
It's definitely part of our future with big data. You know, it's all interrelated. As my college professor, Dr. Adler, used to say, there is no such thing as one subject. It's all subjects together, and math is a part of every subject.
Yeah, we absolutely agree with that. If it isn't, why is it the mainstream subject? We're saying to everybody it is. It's got to be, just like learning English, learn how to write and read is mainstream because it underlies everything else. That's what we're claiming for mathematics. And the mathematics I want to see is one that truly does that, as opposed to being very disconnected, as I think it's often become today. So in fact, we've often been terming other subjects, because you can do computational history, computational biology, all of these things become computational when you think about math in this new way, in a sense, where it's a problem solver for everything. And that's how we're using it in the real world and why it's been so successful.
So my husband is an engineer. He's had engineers work for him. He had an engineer once who claimed they were a, quote, enlightened engineer, which meant they weren't taught calculus. Now, I'll tell you, this particular person was his absolute worst engineer because she didn't understand what a derivative was. So yeah, sure, a computer can do calculations for us, but if you don't understand what you're getting out of it, is that a risk that you think educators are afraid of?
It is a risk. I address that at great length in my book in many different ways. This is a problem we have with the new machinery of AI and machines, complex machines that we work with all the time. What do you as the person, as the human, as the student need to learn? What do we leave to the computer? How do we manage a computer where we don't know how it's working inside? The right way to do that is not to learn how to do everything it does, because then you can't make progress. The right thing to do is to learn verification techniques, to get experience of running this process with complex issues with a computer. And we've rethought the outcomes for math and computation to be able to try to do that. So this is a big hot topic for the future of AI. Don't let the human get fooled. Don't be subservient to the computer. Have the computer be omnipresent but not omnipotent, and let us climb on the power of the computer, but with the safeguards we need. And we need to do much more of this understanding verification in our math. We need to do much more of understanding the way logic works, so we don't get fooled by people saying, is it safe to go back to school? Well, it can never be 100% safe. Science can't prove that it's safe to go back to school with COVID. What it can do is it can assess risk. But we need folks to understand the different options, so to speak, about how you assess risk. How does that mean? Safety, 100% safety can't be proven ever. that's a sort of typical way you need to understand how the computation works. And so to speak, not get fooled by what either a computer coming out with a number says or an expert coming out with a theory says.
Well, here in the state of Georgia, they released data on the COVID cases that the x-axis was not in order by date. So
okay.
And
difficult to read.
So it looked like, there was a trend, and when you took a closer look at the data, it was not a trend because it was not by date. But that's back to the verification. People saying, "Hey, a computer created this," and they're not looking at it with good common sense. And we're making world decisions right now on our ability to understand big data sets and to say, "Hey, let's rerun it a different way." Because you know what? When you're running big data sets, that 1,000th or 10,000th place makes a lot of difference.
One of the things I talk a lot about in the book is knowing when math and computation is helpful, when it isn't helpful, when it can predict things and when it can't. And I think a lot of the trouble we've got with sort of experts, and expertise and the question of expertise at the moment is because people rightly say, well, sometimes people have said, I can predict exactly what's going to happen with math. And you could look at it and say, they can't know that. There are two bigger errors on it. They can't possibly know that. And so then other folks say, well, the maths was completely wrong and useless. So therefore, we're not going to listen to anybody who has any prediction about anything, however reasonable it is. So that's part of, I think, what's failed in our math education. We don't address that. If that's not being addressed in mainstream math education, when you can believe and understand these things, when it's reasonable and not reasonable to model things and so forth, it's very hard for people to evaluate information in society. And that causes some of the issues with what we see at the moment. It's very complicated. There are predictions about COVID that seem to me to be too specific for the data we've currently got. And there are other ones where I see people doing things where I think, my goodness, it's pretty obvious from even rough assessment that maybe that wasn't the right thing to do under the circumstance. And so I think that's an area we really need to help people with in their mainstream math education. And that's what I'm proposing as part of what the changes I would love to see.
So the name of the book is The Math's Fix, An Education Blueprint for the AI Age by Conrad Wolfram. Thank you for kind of giving us an overview as well as relating it to our lives, because this is one thing that I hope that educators come out of this conversation. Math is relevant to our life today. Every day it's relevant to our life, whether we're trying to get physically fit, whether we're trying to help our kids advance, or whether we're trying to teach math or maths, whichever way you say it. Thank you, Conrad.
Thank you. It was great to talk.
If you enjoyed today's 10-Minute Teacher podcast, why not subscribe on iTunes? You can also catch up with Vicki on Twitter at CoolCatTeacher or level up and learn with her blogs and free resources at CoolCatTeacher.com. Thanks for listening.